Hello, and thank you for watching this video. My name is David Burslem. I'm a product manager for Valmet's Boiler Diagnostic Systems Group. And today I'm going to be going over a recent study that we performed at a coal-fired power boiler in the Midwest. They had some issues with fouling in the superheat, and they looked to us to help solve some of those issues. So this study is going to go over that. So let's jump right into it. So I've broken up this presentation into three separate sections. We're going to start off by actually taking a look inside the boiler or inside the furnace into the superheat section with the Valmet infrared imaging systems and Slag Index software. Next, I'll have a brief overview of the acoustic pyrometer technology and then what we actually used for this study. And then finally, we'll take a look at some of the root causes for the problems that were being seen and how we think that those could be improved. And finally, a look at some of the heat rate numbers that we believe to be possible from this. So starting off with some background on the boiler itself that we ran this study on. So this was a 530 gross megawatt tangentially fired unit. It had an SCR, a WFGD, and a cold side ESP. It was using dry high reactivity hydrated lime for SO3 control. And then of course it was burning high sulfur Illinois basin coal. Some of the drivers that that brought about this study and piqued their interest in ours was superheat slagging, so slagging in the upper furnace or fouling. And then of course they were having to use excess soot blower control and stuff to try and mitigate some of the fouling there, which was not actually solving the issue. And then they also wanted to take a look at mill usage at minimum load. So the project itself, we installed 3 cameras, 2 of them being fixed. One was a temporary. They all had our infrared imaging systems with the slag indexing analytical software. And so the 2 cameras that we installed semi-permanently were on the east and west side of the upper furnace looking at the superheat section, so slightly angled up. And we'll get a good idea of that perspective in the next couple of slides when we take a look at that. We also installed a full planar acoustic barometer system, which included 2 acoustic sound generators, or ASGs, and 8 acoustic sound receivers, or ASRs. We'll go over more in depth on the hardware side for the acoustic pyrometer later on in the presentation. Initially, the project was only planned to be about 2 months. But unfortunately, we started this project around the same time that the pandemic started. So what initially was supposed to be a 2-month trial or kind of test that we were planning to do ended up being an over a year-long endeavor. So that turned out to be quite interesting for us and the plant. And of course, the whole purpose for doing this, we wanted to look at some of the root causes for the slagging in the upper furnace, and then why they had such high furnace exit gas temperatures, and then also take a look at the mill deployment impacts. So as I mentioned, first thing we wanted to do when we got involved with this was take a peek into the upper furnace, and so we did that utilizing the infrared imaging systems that Valmet offers. This is actually a snapshot from a video time-lapse report that these systems generate. So these reports are over a 24-hour period of time. They are generated automatically. They can be emailed out, so they're quite small in size. And what this is showing us is we have the infrared image shown kind of in the top center there, and we see some boxes drawn on there. These colored boxes actually correlate to these colored trend lines that we see below it. And these trend lines show the amount of slag buildup inside of those boxes. And so what we see in this image is actually pretty much what we would want to see or expect to see in a normal functioning boiler, where that we have a gradual rise in slag or slag index values, which would mean we're seeing more fouling in these zones accumulate over time, and then we see a steep drop off. And we see that throughout the day a couple of times, especially if we look at this yellow line. Now, as you may have already guessed, this is actually soot blowers coming in and blowing during these time periods of this excess fouling, or the excess shedding of the fouling, I should say. And so, again, this is pretty much normal, what we would expect to see in something like this. So this was our northeast camera. where we're seeing relatively normal functioning. But if we move over to the northwest camera, just a couple 20 feet over or so, we see a little bit different of a story. Now, if you look at that image, you can tell there's quite significant ash buildup or fouling that we see in the superheater section. So we have a huge load of slag or fouling that's built up over time. And if you take a look down at the trend line, you'll notice we have the same type of zones drawn here. And we do actually have some dips, which again are soot blowing events. However, you'll notice it's not the gradual rise and then steep fall. It stays pretty much the same, aside from a little divot when the soot blower comes in. And so what this tells us is that we actually had some very tenacious buildup in this area. And so while it was great to identify the problem with these systems, we knew we had to take it a step further and bring in another instrument to help figure some of this out. In comes the acoustic pyrometer. So this technology is not new. It's actually quite old, and it's been proven for quite some time. And I am by no means a physicist or really capable of explaining the universal gas law and how it exactly relates to what we're doing here. But what I can tell you is that people much smarter than myself have been able to determine that the speed of the sound wave is directly proportional to the average temperature measurement along a given path. And that is the core technology, the core physics behind our system and how we get these temperature measurements. So the actual principle of operation that we see here, again, this is a simplified overview of the process, but what we essentially do here is we have our acoustic signal generator, or ASG. It is filled with compressed air, highly compressed air, and then once ready, it sends a sound wave, a shock wave, across the furnace cavity inside the hot boiler interior. That sound wave travels across and is actually picked up or received by a microphone on the other end of the boiler. And then we can send that signal to our processing computer, where it can calculate that and spit out a temperature number of the average temperature along that path. So the actual equipment that we used for this particular test, or this study, was the Valmet Acoustic Pyrometer system, which again, this is a non-contact measurement device that obtains highly accurate and instantaneous flue gas temperature. And this is typically installed, as was with this test, in the upper furnace, usually at the furnace exit to measure the furnace exit gas temperature. Some of the components include, as we already mentioned, the generator, the receiver, also an air amplifier to build that pressure up to a higher level inside the air cannon, or the ASG. And then of course a control cabinet that houses the processing computer, displays, things of that nature. So next we'll take a look at how these systems are actually mounted to the boiler. So we have two different components that do need to be affixed or mounted to the boiler, and that would be the generator and the receiver. So both of these require some type of penetration, as that sound wave needs to travel fully across and be sent and received by these devices. The receiver itself can usually fit in between the tubes, just right through the membrane of the tube wall, and does not require any tube bends or anything like that. However, the generator itself does require a bit larger of an opening, so about a 3.5-inch opening, which is usually or typically, 2 tube bends. For the temporary nature of this test, we actually ended up fabricating custom mounts that allowed us to adapt these systems directly to the port inspection doors. So we were able to take the existing port inspection doors totally off, and then utilize that existing hinge mount to mount these systems directly onto the boiler wall. And then that allowed us to easily install and remove them when we needed to, when the study finally completed after the pandemic subsided enough for us to go in there. Lastly, one more slide here, just kind of on a system overview. And this is looking at the data and as it flows throughout the system. So pretty simple. Once the signal is processed on that computer after it's been sent and received, it is then sent to a display computer that typically resides in the control room, but this could also live wherever people would want to see this information displayed. That is sent over Ethernet, and then that data can also be passed along to the DCS via Modbus TCP/IP or through a 4 to 20 milliamp analog output box. Now, the whole value of the system really doesn't come from these average temperature paths. It really comes when we add in a second generator, which allows for a mathematical analysis of intersecting paths to give us a true planar temperature measurement. And so as you can see on the right-hand side, this is kind of our standard setup here where we've got 2 different generators and 6 or 8 acoustic sound receivers. And we can see in this next slide here the actual system layout that we used for this study. So you'll notice we have a 3x4 zonal configuration, and we have our ASGs, which would be these red dots located right next to the west and the east side, and the green dots representing our receivers. And then for the sake of simplicity and just to make it a little bit easier to compare the data and analyze the data, we decided to group these AP zones based on their cardinal orientation. So just for example, we decided to call the group of north zones along the north wall the north zones. So quite obvious there, but that would be zones 3, 6, 9, and 12. The west zones would then be groups 1, 2, and 3. So you get the idea, pretty straightforward there, but later on in the presentation, that's how we'll be referring to some of these zones that we are seeing. Next, we have a sample daily report here. And again, this is much like our Slag indexing software that spits out these reports. This is a 24-hour period of time. And what I really like about this report is it gives an excellent view of the fireball's location relative to the walls of the furnace. So as you can see right off the bat, the fireball is not centered. It is actually off to the east a bit and a little bit to the north. And you can probably even tell the orientation of the fireball, how it's spinning. And so again, this is a tangentially fired boiler, and you can kind of see that the fireball itself is rotating in a counterclockwise direction, which does come into play as we look at some of the other data later on, and it explains some of the reasons why we were seeing what we were seeing. So this is an interesting little video here that we just put in to show that while the system is excellent at monitoring conditions at full load, it can also be used or utilized as an excellent startup tool. So this is just a report from a startup or a commissioning that we had done, and this is the boiler coming online, so you can see that even at lower temperatures, this system can be utilized quite effectively. This is a perfect example for me to take a sip of water while I let this video continue to play. All right, another important thing to note here is that unlike some IR pyrometers and things like that, there isn't a low-end temperature that this system cannot read. So we aren't limited to 700 to 3000 degrees F or anything like that, just due to the nature of the physics of the system. So moving along, a question that we get asked quite frequently is, have you verified these temperature values that you're reading against any other form of measurement? And the answer to that is yes. We've measured it against IR pyrometers, and in this specific study that we had done, we actually did a comparison against an HVT, or high velocity thermocouple. So for those that may be unfamiliar, essentially what we did here was took readings in 2-foot increments with the K-type thermocouple that is housed on the HVT. And this just goes inserted into the boiler. And as you might imagine, after we hit about the 4-foot mark, the temperatures came pretty much right in line with our acoustic pyrometer system. So we were within about 0.5% there. Next, we get into some of the more interesting parts of this presentation, at least in my opinion, and I hope in your opinion as well. We decided to combine our data, so the data that we were getting with our acoustic pyrometer, our Slag indexing systems, with that of the plant data. And we did this so that hopefully we could help figure out some of the issues that they had going on. And just to refresh what we had, So we had excess temperatures, so very high temperatures in the upper furnace, specifically on that north zone of the AP system and that west side. And then this side, of course, had that history of aggressive soot blowing in the superheat section, even though it was really not doing much to mitigate those deposits. And so one place that we decided to look, because after reviewing some of the data, we realized that wall blowing was historically neglected or minimized. And so we thought that might be a good spot to start. So that's what we did. Real briefly here, this is a look at the wall blower and soot blower orientation for this boiler. And what we decided to do, much like what we did for our AP systems, is actually put these into groups. So what we did here is group things together based on, again, their cardinal orientation and then their elevation. So for example, if you look over here at the north wall, this top row would be considered 1. The wall code for the north side would be 1. So this would be 11. And then if we drop down a row, this would be 1, 2, or 12. Drop down a row again, 1, 3, or 13. Of course, if we went to the south side, this would be, 3. And so you get the idea. And so the actual time period that we decided to study here, we took about a week-long period of data, and we did a before and after, where essentially we looked at all the before data, and then we decided to roll out a set of changes, some sequencing to these wall blowing events, things like that, so that we could better monitor and compare to what was being done previously. So keep that in mind as we move forward. So one of the very interesting comparisons that was easy to make and caught us a little bit off guard here was the impact that this wall blowing had on specific AP zones, so our temperature zones. So we begin by looking at that set of north zones, so along the north wall. We can actually see here, again, by our grouping of wall blowing codes. So the group that had the biggest impact on temperature on these north zones was actually 1, 3. And if you remember the codes, which I don't expect you to remember, this would be the north side, and this would be actually the third row down of wall blowers had the biggest impact. So contrary to what we thought, which would have been that the top rows would have all had the biggest impact, if you look 1, 3, 4, 3, 2, 3, 3, 3, these all had pretty significant impacts on the temperatures. And so we found that to be quite interesting, why something so far down was causing such a big impact. And we saw the same thing as we looked at the west AP zones. So again, 1, 3, 2, 3. So again, this third row, which again is, our AP systems are right in line pretty much with this first or top row. In between this top row and the superheat section is where the AP system lived. And so it's quite interesting to see that all the way down here had the biggest impact on the temperatures for that system. And so we figured, well, it was probably due to fouling, and then that causing some issues with the heat transfer and causing the temperatures to just stay in the gas. And so that was what we thought. However, we weren't exactly sure at the moment, but what we did find was a solid correlation between the specific wall blowing groups and then changes in wall associated quadrant temperatures, so our northwest temperatures, etc. And then I guess not to our surprise, but maybe a little bit to the surprise of the plant at the time, they did do a drone survey of the furnace walls after a shutdown after this study, and it showed significant buildup of wall deposits on that third elevation. So that was good, good in the sense that it verified what we were seeing there, bad in the sense that, yeah, the plant had some issues with the fouling in that area. And so after that, the plant decided that they would do increased wall blowing, because again, historically this had kind of been minimized. And so especially when they saw higher temperatures in the furnace exit, they decided that they would be increasing their wall blowing there. And so that's all quite interesting. I think that alone is probably enough for a presentation, but we did want to take it a little step further and talk about the impact this might have on, say, heat rate. And so one of the easy things to look at, I suppose, is because we had better control over the FEGT and the impact that has on steam temperatures, we could take a look at how the temperating sprays were being used after these changes were made. So specifically looking at the reheat side, after discussing with this plant a little bit, we found out that if the valve for the temperating sprays was fully open, that'd be about 75,000 pounds per hour of spray. And now after these changes, as you can see, if we average this out, it's about a 15% reduction in spray, or 12,000 pounds per hour, that was saved just in this small window of time. Now, that's a pretty significant number, and so talking with the plant and taking, I would say, a very conservative approach here would suggest some averages closer to about 2,000 pounds per hour. And again, this is going to be site specific, but if we look at what's been stated in literature and just say that, 2,000 pounds per hour can equal out to about 20 BTUs per kilowatt hour, and we compare that to a nominal 10,000 BTU per kilowatt hour, that would equal out to be about a 0.2% improvement in overall heat rate. And we can take a look at this in a slightly different way. So this was some more data that we found while we were doing this analysis. This one is quite interesting because it looks at basically the amount of coal being used to generate megawatts. And what we saw was a drop in the amount of coal being used to generate the same amount of megawatts each time the wall blowers were being ran. And so as you can see here, this was about a 0.0075 pounds per megawatt hour that was being dropped in fuel use each time these wall blowers were being ran. And so if we do the math on that, averaged out over a full cycle, this would give a projection of about 0.4% improvement in heat rate. So in conclusion, we brought in the infrared imaging systems with our Slag indexing software, and that allowed us to immediately identify the issues and the location that we were seeing with the superheat fouling. We then used our Planar AP system to successfully identify the excessively high north and west gas temperatures that we were seeing in the AP system, or I should say in the furnace, which of course are natural precursors to what we were seeing with the superheat fouling. And then finally, we used a multivariable analysis to reveal these patterns between wall blowing actions and then gas and steam temperatures. And with that data and some intelligent SIP blowing controls coordinating some various elevations of wall blowing allowed us to demonstrate a short-term improvement in heat rate, specifically with, again, the reduction in reheat temperating sprays being used, and then of course, the amount of coal being used to burn to generate megawatt hours. So overall, quite interesting and about equaling out to 0.6% improvement in heat rate. So of course, a huge thank you to the plant staff and the corporate staff that allowed us to perform this study and supported us throughout the difficulties of the pandemic years. Feels bad saying years there, but that's the case. And so again, thank you very much for those folks for allowing us to do this. And then of course, big thank you to Cal Lockhart, who spearheaded this effort and got a lot of this information together for us. So again, thanks to everyone involved, and thank you for watching. Very much appreciate it. If you have any questions or comments, please don't hesitate to reach out to anyone at the Valmet Boiler Diagnostic Systems group, and we'd be happy to answer your questions. Thank you.